We live in a world surrounded by satellites. They orbit the Earth, move thousands of kilometers per hour, and send important information about our environment back to the ground. Allan Shtofenmakher is a graduate student at MIT's Department of Aeronautics and Astronautics who works to keep this environment clean and sustainable by preventing collisions in space.
Hi, folks, and hi. Thank you, Fatima, for that warm welcome, and thank you all for being here today. My name is Allan Shtofenmakher. I am an MIT PhD candidate, and today I'll be telling you a little bit more about myself, who I am as a person, some of the cool stuff that I've done over the past few years as an aerospace engineer, why space is important, and why it's important to avoid collisions in space. So I'd like to start by explaining what a PhD candidate at MIT is and does. And it sort of comes down to two things. Everyone's experience is a little bit different, but I am doing research in engineering, which means I'm working to solve challenging problems that don't really have solutions that we know yet. And I'm surrounded by people who are a lot smarter than I am, who can teach me cool things about topics I know nothing about every single day. It's great. It also means I am a graduate student, which means I'm still in school, just like you, and I also have to take classes, whether I want to or not. And finally, it means I'm an aerospace engineer, which also comes down to two things. I do stuff in air, and I do stuff in space. And on the right is a picture of me at my desk in my lab on MIT's campus. So how did I get here? Well, when I was born, I was actually the youngest person in the world for just a few seconds. But I think we should probably skip the first few years and just jump to where I went to college. In Southern California, I went to the University of California in Irvine, where I did my bachelor's degree in aerospace engineering. After that, I graduated and I went to Boeing to work on unconventional aircraft designs. And after that, I went back to school to Stanford University in Northern California, where I did my master's degree in aeronautics and astronautics. After Stanford, I decided I needed a break from school, so I went to work at a satellite startup called TIVAC, or Terran Orbital, for a couple of years. And there I worked on a number of cool satellite programs, a couple of which I'll talk to you about on the next slide. While I was at the satellite startup, I realized there were some problems that I was interested in solving that were best approached from an academic setting, so like a school or a university. So in my last year at the startup, I applied to a couple of PhD programs around the United States. And from there, found myself doing a PhD at MIT, which is how I'm here today, presenting to you as part of MIT Abstracts. So it's been a journey. At this point, I've been an aerospace engineer for about 10 years now, which basically means that I have a few cool projects that I'd like to share with you today on this slide. So one of the ones that I'm most proud of, and let me turn on the laser pointer here, is in the top left here. It's a system called the Terabyte Infrared Delivery, or T-Bird for short. And it is a laser in space that holds the Guinness World Record for the fastest transfer of information from space to the ground. In a single 5-minute pass, it was able to transmit 5 terabytes of information using a laser that went through hundreds of kilometers of free space. For context, 5 terabytes is over 1 million photos on your phone, or over 100,000 hours of music, or thousands of hours of HD video, all in 5 minutes, which is really fast. If you wanted to know what that sort of satellite would look like in person, if you walked up to it, this picture in the middle is sort of what that would look like. It's about as tall as a shoebox on its side and about as wide as you might be if you stuck your hands out and tried to measure your wingspan from tip to tip. One thing I just want to point out here is that on this satellite here in the bottom left corner, we have a camera. As it turns out, most active spacecraft on orbit today have some of these cameras, whose main function is really to just look up at space and look at stars and take pictures of them. By taking pictures of stars, you can compare the pictures you took with maps that you have on your onboard computer and use that information to figure out how exactly your spacecraft is pointing in space. But it turns out you don't have to just use them to look up at the stars. You can also use these cameras to look off to the side and see what else is around you. And that kind of teases some of the work that I've been doing here at MIT, which I'm really only going to present in this one little animation, but happy to answer questions about it later. But here, we have a constellation of satellites in space using their cameras to keep track of other satellites and space junk that are around them. So the focus of today's talk is, of course, going to be about space, but I do want to give a shout out to some of the other stuff that I've worked on. When I was at Boeing, like I said, I worked on unconventional aircraft designs, and one of the things that I worked on was something called the blended wing body, a picture of which you can see here in the bottom left. A blended wing body is different from your traditional tube and wing airplane, which has, yes, the wings that generate lift, but also this big old cylinder that's primary purpose is just to carry passengers. It doesn't do a whole lot for lift or aerodynamic efficiency. The blended wing body takes that cylinder and fuses it with the wings of the plane so that the entire aircraft is just one big flying wing, which means two things. It's a lot more efficient than your traditional airplane, but it's also a lot more complicated, which makes it that much more interesting and fun to solve. After Boeing, I went to Stanford, and at Stanford, one of the things I worked on was a CubeSat. For those who don't know, a CubeSat is a pretty small, inexpensive satellite that you and a few other students who maybe don't have a whole lot of money can put together and then ask NASA nicely, hey, you're sending up a big rocket in a couple of months. Would you mind also sending up our tiny little CubeSat with you? And if they say yes, then the tiny little CubeSat you made with your friends could be up in space doing cool space stuff. In undergrad, I worked on a goofy little robot that had a tire on top. Basically, the idea was we pump the tire up full of air, and then the robot uses the air in the tire to propel itself along an obstacle course and make its way to the finish line. And finally, in the bottom right is a picture of a lunar lander design that I worked on when I was at the satellite startup. So to answer my own question, what have I done along the way? Some air, some robots, mostly space. Why? Because space is cool. But space is also important for a number of reasons, but it can be summarized in one sentence. We can do things in space that we either can't do or can't do well on the ground. And I think one of the best examples of this is science. This picture in the top left, you might be familiar with, is the Pillars of Creation, which is one of the most well-known photos ever taken by the Hubble Space Telescope you can see at the bottom left. The Hubble Space Telescope is, to simplify things a lot, basically a very nice telescope on a satellite in space. But we have very nice, very big, very expensive telescopes on the ground, but they can't take pictures of things like the pillars of creation as well as a telescope in space can, because telescopes on the ground have to look through light that's coming through the atmosphere, but telescopes in space don't need to do that, so they can see a lot cooler stuff. And similarly, astronauts, space is where astronauts do their astronaut stuff. So when they're on a space station, sometimes they have free time to take cool pictures of the Earth from space or play the saxophone. But most of the time, most of their waking hours are spent doing experiments in microgravity that you just can't do on the surface of Earth at its full gravity strength. Beyond that, one of the coolest things we do from space is weather monitoring. This is a picture of a hurricane taken from space by a satellite. And if this morning you woke up and looked at the weather forecast either on your phone or on the TV, chances are that forecast used data that came from a weather satellite. And last but definitely not least, GPS is only able to work because of satellite constellations that we have in space. So the next time you whip out your phone to figure out where you are or where you're going or how you're going to get there, make sure to think a satellite. So the thing, like, space is important for a lot of reasons, but one of the things that sort of binds all of the things that are on this slide together is that they all use satellites. Satellites are the mechanism by which we can do so many cool things in space. So how do satellites even get up there in the first place? Well, usually it involves some kind of rocket. In this case, I've got a massive rocket off the coast of Alaska, and inside that rocket is its payload. In this case, a blue little satellite that it's going to try to deliver to space. It's going to launch and go really fast, several hundreds of kilometers up into space. And when it's where it needs to be, it deploys our little blue satellite payload, which then goes about doing its day-to-day thing. Because there are so many cool things in space, we're starting to send more and more satellites up there. And as a result, space is getting crowded to the point that now it's a concern as to are things going to start crashing into each other. The latest numbers that I have are that there are over 10,000 active spacecraft in orbit, and that includes things like the International Space Station, the weather satellites, and the GPS satellites we talked about a couple of slides ago, and all of the active Starlink satellites in the Starlink mega constellation. But those aren't the only things in space. There's also defunct spacecraft and space junk and micrometeoroids that are cluttering the space environment to the point that we have over 30,000 objects, about the size of a softball or bigger, that we can reliably track using sensors that we have on the ground. And it's important to be tracking those because if not, we might have a lot of collisions. There are 600,000 plus collision warnings every day, and that's only among objects that are in this 10 centimeter plus class. This does not include the over a million even smaller space objects that are just too small for us to reliably track using the technology that we have. And because space is so crowded, accidents can happen. And when things collide in space, that generates a lot of space debris, which is a problem. Why? Well, I'm going to start again with the animation we had 2 slides ago. Let's say we just let those two spacecraft crash into each other. Cool. What happens next? That generates a lot of space debris. Where does that space debris, excuse me, go? Some of it might return to the atmosphere, but most of it is going to stay in space, moving at thousands of miles an hour until eventually it crashes into something else. And that generates more space debris, which crashes into other things, which generates more space debris, which crashes into other things, and so on. If this happens enough times in a short enough period of time, space may become unsustainable for day-to-day satellite operations. This is something called Kessler syndrome, and there are hundreds, if not thousands of people, including myself, working very hard to try to prevent this from happening. How do we go about actually preventing collisions in space? Well, starting with, whatever the space environment is at a certain time with all of the 30,000 plus objects in it, it usually starts with using sensors that are on the ground to track these space objects. I'll talk a little bit more about the sensors that we use on the next slide, but the idea is we ask these things to look up at space, find these space objects, and collect information like where are they and where are they going? And then they feed that information to a computer simulation that looks for potential collisions between any two objects that we have data for. If the risk of collision is high enough, we'll send a little notification to the folks who are operating those spacecraft. We hope, will send up a command to their spacecraft, which will then perform a little maneuver to, fingers crossed, avoid a collision. And then that happens many, many times every day. My focus here at MIT is on improving the way we use sensors to track objects in space. Now, like I said, a little bit more on the sensors that we actually use to keep track of these space objects. There's quite a few that we use, but I'm going to present two of the most common ones on this slide. The first of which I think we all might be familiar with. Telescopes. The same telescopes that we can use to look up at the stars or galaxies in a night sky, we can actually use to look at satellites and space junk, as long as those satellites are big enough and bright enough. The thing is, telescopes really work their best at night. So when it's daytime, we need another system that's able to keep track of them. The most common of which uses a technology called radar. And radar was something that was developed here at MIT many decades ago, and it's a complicated system, but the gist of how it works is it blasts electromagnetic radiation up into space, which bounces off any objects that it hits. I'm going to play that again because I really like this animation. It bounces off any objects that it hits, and we can use the information, the signal that comes back to us, to get very good estimates of where these objects are and where they're going. But that's only half the problem because we've only got a handful of sensors and tens of thousands of space objects that we need to track. How do we choose which objects to track and when to track them? This is one of the questions that I've been trying to answer over the course of my PhD. And to answer this, we sort of took inspiration from something that I hoped we can all relate to: ordering pizza. For me, it's easy enough to order pizza by calling up the local pizza place and saying, hey, could I please have, a medium pizza with these toppings, a large pizza with these toppings, and some breadsticks. And 30, 40 minutes later, I'll open my door and I'll be happy because I have my pizza, and the pizza delivery driver will be happy because I gave him a big tip. Um, but it's actually a much harder problem for the pizza folks because they're not just delivering to me. They've got dozens of places that they need to deliver to every night, and only a few cars that can actually deliver those pizzas. So, how do they best go about delivering or dividing and conquering the map so that they can deliver all of the pizzas they need in the time that they have, while minimizing the amount of money that they spend on fuel? As it turns out, the solution to this problem is actually very similar to the solution of tracking space objects. Instead of pizza delivery trucks, we have sensors. Instead of pizzas to deliver and houses to visit, we have objects we need to track. But the question is essentially the same. How do we best divide and conquer the map so that we can, for example, track as many space objects as possible in the minimum amount of time? The biggest difference between delivering pizzas and tracking space objects is that when you deliver pizzas, the houses you're delivering to don't usually move. In space, everything is moving very, very fast, and that makes the problem just a little bit harder. But it also means it's that much more interesting to solve. So where does this fit into the overall picture? I've shown this slide before. I spent the last 5 minutes talking about the way that I'm trying to improve the way we use sensors to track space objects. But the idea is we want this to feed into improving the way we detect collisions and operators choose to do maneuvers so that in the end, we can avoid collisions in space. And so that more or less does it for the sort of stuff that I wanted to talk to about aerospace and what I do for research here at MIT. I'd like to leave us off on one last slide that talks about what else I do in my ample spare time. I got into aerospace engineering because I really liked making paper airplanes when I was a kid. I'm definitely more on the space side these days, but every once in a while, I'll still make a little paper airplane. It's always good fun. I skate. There's a picture of me doing an ollie. Since I came to MIT, I got into mixology and archery. So there's pics of a coffee drink and me next to some of the arrows that I've shot on the left. Other stuff that's not pictured here, I like reading, mostly fantasy and science fiction. I like traveling. I was in Ireland this past May. I'm probably going up to New Hampshire this weekend to look at the fall foliage. I like escape rooms and a bunch of other things. So I'll leave this up. With that, I'll pass it back to you, Fatima, to run Q&A. Thank you so much.
Thank you very, very much, Alan, for a fantastic presentation. To kick us off, we have a question from Lucia, and Lucia is wondering what inspired you to learn about space? So you mentioned the paper airplanes brought you into aero, but how did the space element come in?
Well, actually, I'm gonna go back to this slide here real quickly. The answer is this little CubeSat right here. Back when I was, and thank you, Lucia, for the question. I really like this one. Back when I was in undergrad at UC Irvine, I actually only took one space class. I took a lot of classes on aerodynamics and fluid mechanics, and I thought I was going to be a plane guy. And then when I went to Stanford, I got to work on actual space projects, and I'm like, this is so cool, and decided I'd probably spend the rest of my life working on it. Thank you for the question.
Got it. Well, we have a follow-up from another Nord Anglia student who's wondering how much time does it take to make a satellite? Maybe you can tell us about how long it took to make that CubeSat.
So this CubeSat was a year-long program, more or less. It was, a few classes distributed throughout an academic year, and teams of, a couple dozen students would work on either the structure of the CubeSat or the software and things like that. They're usually not that fast. Some of the CubeSat ones can be delivered in 9 to 15 months. Some satellite programs take years, if not decades. I think the James Webb Telescope took 2 to 3 decades. I'd want to double check that, but anywhere from a few months to a couple of decades.
Goodness, that's quite a range. Now to follow up on more satellite related questions, would it ever make sense to make satellites more protected against collisions? Is that even possible, or is that speed too
Yes.
fast, regardless of any protection?
No, yes, that's a great question. There are folks doing research on essentially armor for spacecraft so that they can, survive collisions with some of the smaller objects, less than the size of a softball, excuse me, that are tough to track from space. There are um, coupled problems with putting armor on spacecraft because with space, mass is usually one of the most important things we care about. When we put armor up, that makes the spacecraft that much heavier. And it also might make it harder for the spacecraft to collect energy from the sun if the armor is protecting the solar panels. And it might make it harder for the spacecraft to stay warm or cold. If the armor is blocking the thermal system. So it's an ongoing set of projects to figure out how to put armor on spacecraft.
Our Nord Anglia student Anshul asks and has an idea to float here. Anshul asks, can there be a new satellite where it doesn't just dodge debris, but maybe has a laser to obliterate the debris coming its way?
Yeah, that's a very good idea. Thank you, Anshul. I'll make sure to pass that on to NASA. There are definitely folks working on lasers on the ground to blast space debris out. I think a laser that's in space trying to blast nearby space debris has two problems. It needs to know exactly where that space debris is, which might be hard to figure out if that space debris is coming at you at thousands of miles an hour so that you're fast enough to respond. And lasers can require a lot of energy, especially if they're strong enough to break things in space. But I do think folks are working on it on the ground. They may also be working it on satellites to have lasers to break debris.
Got it. And in the meantime, we're wondering with the tools we already have and related to your project and your research, Nord Anglia student is wondering how quick is that detection, alert, maneuver process to prevent these objects from colliding?
Yeah, that's a great question. I would say that the timeline is typically on the week span, where a week in advance, the computer system will say, "Hey, we think you might have a conjunction or near miss with another spacecraft over here." Operators of spacecraft usually request that they get their last bit of information 72 hours in advance, so 3 days, so that that gives them enough time to perform a maneuver, assess whether or not the maneuver was successful in avoiding the collision, and maybe give them enough time to go again. For the most important spacecraft, it might be something done in the span of like an hour or two, but that requires reprioritizing a lot of resources.
Got it. And Anya's wondering, is there a particular spot in space that's best to avoid collisions?
Um, Oh, I know that one of the spots that is at greatest risk for collision is over the North Pole and the South Pole. It's a function of orbital mechanics, but basically, if there are satellites in polar orbits, so 90 degrees inclination, they all will more or less go directly above the North Pole, which means there's a much higher risk of colliding there than really anywhere else over the Earth.
Interesting. And Isabel is now wondering what would happen if you accidentally were tracking the wrong object in space? How do you know you're tracking the right object to begin with?
Thank you, Isabel. No, these are really great questions. What you're touching on is a problem called track correlation. And oftentimes we actually don't always know what object it is that we're looking at. So what we'll do in those cases is usually we have to look at an object like several times in order to be confident that it's the same object each time we track it. But then we'll trace it back to maybe recent launches that have happened or recent collisions that have happened to be like, okay, we're 95% confident this is this spacecraft from this launch or this piece of debris from this explosion.
Got it. Well, and now Going on to debris from Tiana. Tiana's wondering, how do we even detect the debris from space? Do you have satellites tracking debris itself, or is it only focused on these active satellites?
We actually pretty much track them using similar technologies to how we track the satellites. Really, the benefit of having active satellites is that you can work with the people who are running the satellites, so they can tell you, "Hey, we think our spacecraft is here. Is that consistent with the information that you have?" And then that confirms, okay, yes, this thing that we're looking at is Starlink 1, 2, 3, 4, 5. Um, but with the debris, we don't have that confirmation, so we just rely on the radars and the telescopes to be like, okay, we've seen this one piece of, we don't know what it is, 5 times now. We're pretty sure it's this piece of debris from this explosion. Let's just keep tracking it to make sure it doesn't crash into anything else.
Wow, and how many collisions, happen realistically? We don't really have a sense for that here.
Yeah, so not as often as we have collision avoidance messages, thankfully. Uh, Really, the one big collision between spacecraft happened almost 20 years ago in 2007 between a US Iridium satellite and a Russian Cosmos satellite. And that collision between two objects generated over 3,000 pieces of debris. So since that's happened, we've gotten a lot more proactive about preventing collisions in the future. Now, small collisions between those objects that we can't that are smaller than the size of a softball happen quite frequently. And I'd say every couple of months, the International Space Station says, "Oh, we have a new dent in our hull. We think this was from a tiny little micrometeoroid," or "Oh, we have a leak in a pipe on the outside of the spacecraft that was probably from a piece of space debris." So the small collisions fairly frequently, big collisions not that often.
Got it. And Anya is wondering, how long would it take to eliminate all the space debris from those collisions that have happened right now?
Sorry, could you repeat the question?
How long would it take to eliminate all the space debris that's currently up there? What do you think?
Okay. Um, so here's I'll start with correcting a misconception. People say there's no air in space. That's not exactly true. There's actually very, very thin air in space. The atmosphere, the ending of the atmosphere is sort of not exactly well defined. So objects in space that are below about 600 kilometers in altitude above the Earth will probably eventually come down within about 25-ish years. It depends on how big they are. And that's largely because they're crashing into these air molecules in space, and that friction slowly takes energy from them and brings them back down to Earth. Above 600 kilometers, it would probably take hundreds of years, if ever, for those things to come back down to Earth.
Wow, that's a really long time.
Yeah.
Goodness. Tiana's wondering, can we bring space debris down to Earth intentionally and make it go through Earth's atmosphere where it vaporizes?
Well, thank you, Yana. Y'all are asking all the right questions. Folks are actively working on a concept called active debris removal, which is essentially sending a satellite up into space to catch some of these debris particles and bring it back down to Earth with them. There are a couple of companies that have started that are trying to prove that that concept works. But maybe we'll see in 5, 10 years, we might have systems out there that are actively bringing debris down into Earth's atmosphere.
We can hope.
We can hope.
Another student is asking if there is enough debris accumulating in space and it doesn't get removed, so maybe it's above that altitude threshold you mentioned, would it
Mhm.
eventually form rings like Saturn?
I am not an astrophysicist, but I suppose if there's enough debris in that area and they crash into each other enough times, you very well could get a debris ring. I'm not an astrophysicist, but that's just my guess.
Got it. I feel like even in the ESA picture you showed describing it, it almost looks like
Yeah,
rings of satellites there. So I
it
imagine
kind of
it could
does.
be, yeah.
Yeah.
Rosa's wondering, what is the life cycle of a satellite in space?
Mm. Thank you, Rosa. Well, it starts with launch. You send your rocket up into space that's holding your satellite. Your satellite gets deployed, and then it goes through a process called checkout, where essentially, it speaks to the operators on the ground for the first time. The operators send their first commands up there, and they're like, "Okay, everything looks healthy. Let's keep going." And then, depending on what altitude it's at and what its mission is, it could operate for anywhere from a couple of months to decades, doing its normal mission until, either something happens and it doesn't work anymore, or the operators decide, okay, it's time. We should probably retire the satellite. And if it's close enough to the atmosphere, we bring it back in with the thruster burn so it burns up and doesn't produce more trash. But if it's too far away, we put it in something called a graveyard orbit, which is an orbit where not a whole lot of stuff is going on. So we don't care that much if there's debris there. Um, I think in the near future we will decide we do care about that. But right now we have graveyard orbits as a solution for retired satellites.
Got it. And before we switch over to another line of questions about your educational background, I wanted to ask one more quick satellite question that a couple of students in the Q&A pod have asked. And they're wondering, with your research as it develops, is the hope in the future one day that the system will be automated and doesn't require humans to assess whether a collision is happening and satellites can decide to move out of the way on their own?
I certainly hope so. Um, I believe, in fact, that SpaceX's Starlink constellation has already implemented that in some way, just because I think they actually just recently crossed the 10,000 satellite threshold in space. And so it would just take too many engineer hours to manually avoid collisions. So I think they already have an automated process where they take in you know, the collision notification warning, and they use that information to automatically decide if they need to do a maneuver to avoid a collision. But outside of the one company, I'm hoping that there will eventually be, a higher level of automation so that that's, across the entire Earth space environment that's automated, but it's not there yet.
Okay, fingers crossed for the future on multiple fronts. Now I want to switch gears a little bit to answer some of the questions that the students have been asking about your educational background and journey to AeroAstro. And so Isabella's wondering, were there any particular classes in high school or middle school that you think help you the most in your research today?
Um, I guess all of the math classes and the physics classes that I took, surprisingly, geometry and trigonometry, have been helpful, especially for like back of the envelope two-dimensional calculations. The amount of sines and cosines that I've had to do at this point in my education has been surprising. So if you're interested in getting into something like this, I'd recommend paying attention in your math and like your physics classes. But beyond that, if now or in high school you still decide you want to get into this, getting involved in projects like CubeSat programs or even robotics or design, build, fly airplane programs, those I think all look well on a college application for an aerospace program.
Are there resources online where folks can learn to get started making their own satellites? We have a couple of questions saying, how do I make a CubeSat?
Um, the first suggestion would be find someone who's already made a CubeSat and ask them for support. There is a NASA CubeSat 101 online, which if you're interested in, it's like 100 pages, but if you really want to, you can look through that and learn the concepts required for making a CubeSat. And then it could be you find a teacher at school who's willing to sponsor, or a professor at a local university who's willing to send y'all funds and start up a CubeSat program at your school, and then things will go from there.
Excellent. And speaking of a teacher there, Dan is wondering, did anyone in particular inspire you to study aeroastro, maybe a professor or a teacher along the way?
Um, when I so a person, the answer unfortunately is no. It was really just I was, in my final year of high school, I was like, I don't know who I am as a person. What do I want to do for the rest of my life? And I looked under my bed and found the bags of paper airplanes that I had, and I was like, oh yeah, yeah, that's a good idea.
Goodness, I mean, that's a pretty cool story, and it's interesting that you were collecting all of them for sure. So now we're wondering so you mentioned that your physics and math classes in particular, the skills you learned in trig and geometry are really, really relevant to the work you do today. But Isabel is wondering, what was your favorite subject in school?
I really liked geometry and calculus. I also took AP Physics, and that was really cool, but I think mostly because the teacher was really cool, and we did like demonstrations and stuff, and I'm like, wow, this is science. But yeah, geometry, calculus, and physics.
Got it. And now we have a question from a Nord Anglia student who's wondering, um, what is your sci-fi book recommendation for this
My
audience?
sci-fi book recommendation for this audience. Um, I might have to think about that. Let me look through my Audible readings here. Oh, yes. The Hitchhiker's Guide to the Galaxy. There we are.
Good one.
Yeah.
Excellent. And another follow-up question from Amber related to your academics. Are there any misconceptions that you'd like to address for anyone who's interested in studying aeroastro? What should folks know?
Misconceptions, Aeroastro. Um, I think one thing that I would have liked to have clarified when I was choosing a school to go to study aerospace engineering was to what extent is the focus of the program on air versus on space? And I, sort of picked the school for other reasons. But I if my undergrad institution had more classes on astronautics, I think I would have found my way to space a little bit sooner.
Got it. And so we have so many excellent, awesome questions still in the chat, but we only have time for one more. So I think that there's so many students here who are interested in perhaps pursuing aerospace engineering or building satellites one day. I wonder if you can leave them with some advice as they pursue this. You've already mentioned the classes, but what advice would you give folks who are interested in pursuing this particular challenge?
Yeah. So like I was alluding to earlier, if you're sure this is the path that you want to go down, or even if you're not sure, but you just want to try it out, I think one of the most significant things you can do now or in high school is to get started on a project that features aeroastro concepts in some way. So I know that there's a lot of robotics programs out there. This might be a hot take, but airplanes and satellites are kind of just like special robots, right? So if you get involved in robotics, that is directly applicable to certain parts of airplanes and spacecraft and rockets. Um, it's fairly doable to get involved in like sort of uh, putting together your own like foam aircraft and putting RC parts in it so that you can remote control a little aircraft that you built yourself. Getting into space stuff is a little bit harder, but like one of the students asked earlier, if you're really about it, I'd recommend reaching out to a teacher or a local college professor and say, hey, I want to get involved in a CubeSat program. Do you have one going on right now that I could possibly join? Or maybe would you be willing to start a program with my school so that we can have, dozens of students working on this one little CubeSat that we'll name after our school and also you.
Excellent. Thank you so much for that advice, Alan. Now, before we go, I just wanted to remind our abstract listeners that we have a few exciting abstracts to come as well. So I'm really looking forward to seeing you all there. And to end, I'd like to thank everyone for joining us today. I want to thank the students for asking such awesome, curious questions, and thank you to the MIT Nord Anglia Education Collaboration for making this series possible. And thank you very much, Alan, for sharing your research and insights with us today.
Thank you for the invitation. This has been a blast.
Wonderful. Okay, see you all next time. Goodbye.